So the goal in this video is for us to begin to understand how to use deductive reasoning. Basically, we have to have a reason for everything we say. And in Chapter 2, these are going to be the reasons we're going to be using. So first of all, we have segment addition. Now, the way you recognize segment addition is it's two segments make a big segment. So two segments make a big segment. When you look at the picture, I'm adding AB and BC to get AC. So two segments make a big segment. Angle addition, same idea but with angles. Two angles make a big angle. ABD, the top angle, plus the small angle, make the big angle. Angle addition postulate and segment addition postulate. Those are postulates we use to add segments and add angles. Addition property of equality. This is what we do in algebra when we add 3 to both sides of an equation or subtract 10 from both sides of an equation. But in geometry, we're usually using segments or angles, and it looks different. It's kind of confusing because it looks so different. But here's what I'm trying to get you to understand. That like when we add 10 to both sides, we're adding the same thing to both sides. See here how we added CD and DE to both sides? CD and DE are equal. We're really adding the same thing to both sides. Doesn't look like it because they're different letters, but they're the same length. They're the same number. I'm adding the same number to both sides. Another example, subtraction property of equality, same idea. CD and DE are equal, so I'm subtracting the same thing from both sides. Okay, look at these carefully and make sure you recognize it. And notice how there are 4 segments in both cases, and we could do this with angles too. Don't confuse this with angle addition. Angle addition is 2 segments make a big segment. This is, I'm adding the same thing to both sides. Even though those things don't look the same, they're equal, so I am adding the same thing to both sides. So notice that there's no segment subtraction. It does not exist. We don't need it. That's why it doesn't exist. We don't add things we don't need when we prove in proofs. We try to keep the reasons as small as possible. Division property of equality, that's when I divide both sides by the same number. Multiplication property of equality, that's when I multiply both sides of the equation by the same number. Substitution, probably one of the most common reasons in geometry. When you run to one of these proofs on state tests, probably a good part of the time, substitution is going to be the reason. Substitution is when I plug something equal in another spot. So we've got AB equal to EF. That means I could replace AB with EF. So I'm going in this statement and replacing AB with EF because AB equals EF. They're the same thing. So when I replace AB with EF, I get EF equals BC plus CD. Substitution can look a lot different in different situations, but it's the same idea. I'm plugging something equivalent in another spot because they're equal things. Reflexive property of equality. The reflexive property is that anything's equal to itself or congruent to itself. Seems like a silly thing because it's kind of obvious. It ought to be equal or congruent to itself, right? But we use this in proof to get a segment in our proof that we need in certain situations. You won't use this so much in Chapter 2, but later on when we prove triangles congruent, we use it a lot, and it'll make sense in that situation. But you do need to know what it is now. Reflexive property, anything's congruent to itself or equal to itself. The transitive property, I just don't use as a rule. I generally just use substitution. Technically, substitution is a property of equality. However, in my class, I'm perfectly okay if you substitute with congruence. I'm not going to make you take another step and say they're equal first. So, transitive property kind of looks like something you've seen before in the law of syllogism. AB is equal to BC, BC is equal to CD. So it's kind of like substitution. I could replace AB with BC, and right here I'll replace it, and I get AB equals CD. So we can use the transitive property with both equal and congruent segments or angles. But as a rule, I'm going to stick to substitution. So I'm just pointing out that this thing exists. We won't use it very much. The linear pair theorem. If two angles form a linear pair, then the two angles are supplementary. We use that a lot. So basically, if we have a situation where like angle 1 and 2, they make a line together, a linear pair, line being the root word, that means the two angles add to 180. They're supplementary. This is a reason we use. You need to know it. Definition of midpoint. Another really common reason. A point is the midpoint if and only if. Hey, notice that biconditional thing going on. This is a definition. A point, I need points here, not arrows. A point is the midpoint, so there's my midpoint. If and only if it divides the line into two congruent segments. Now notice that's a biconditional. We could turn that around and say, hey, if a point divides a segment into two congruent segments, then it's a midpoint. And we could use the contrapositive and the inverse too. Generally, we use the inverse and converse with biconditionals and definitions most of the time. Definition of angle bisector. Again, there's that if and only if. Every definition can be a biconditional, a true biconditional. So a ray bisects an angle. It cuts it into two equal parts, so there's angle 1 and 2. And if this is ray AB that bisects that angle, then angle 1 would be congruent to angle 2. So that's a biconditional. We can turn it around and use the converse. If a ray divides an angle into two congruent angles, then the ray is a bisector of the angle. Definition segment bisector. Notice the conclusion here that it's a midpoint. So the definition states that it's the midpoint. A line is a bisector of a segment if and only if it passes through the midpoint of the segment. So if I use this in a reason, what I'll be concluding is that a point is the midpoint. It seems strange, but that's the conclusion. But as it's a converse, we could say, hey, if a point is a midpoint and that line passes through it, then it's a bisector of the segment. Now, it could be a line, it could be a ray, it could be a segment that bisects another segment. Definition of right angle. An angle is a right angle if and only if it has a measure of 90. We know that one. Definition of supplementary angles. Two angles are supplementary if and only if their measures add to 180. So we could turn that around. If they add to 180, then they're supplementary. Definition of complementary angles. Two angles are complementary if and only if their sum is 90. So if their sum is 90, then they're complementary. That's the converse. So there are a lot of reasons here. This is the last page, though. Congruent supplements theorem is not one we use very often, but basically it says that if two angles are supplements of congruent angles, so imagine, let me put a number in here. If I had 120 and 60, 120 and 60, do you see how 120 and 120 are supplements of angles that are both 60? Now, it's obvious with numbers, but when I put an angle in there and I go angle 1 and angle 2 are supplementary, angle 3 and angle 2 are supplementary. Well, since 2 is the same angle, like they're both 60 degrees, angle 2 is in both cases, that means 1 and 3 would have to be congruent. So we'd know that angle 1 would be congruent to angle 3. That's what the theorem's saying. It's not something we use that often, but when you put in numbers, it's much more obvious. That's the problem. Congruent complements theorem is the same idea. If I had a 60 and a 30 and another angle, different angle that was 60 and 30, but see these two are the same angle, and I know that the 60s have to be congruent. So if angle 1 was complementary to angle 2, and angle 3 was complementary to angle 2, then that would mean that angle 1 was congruent to angle 3. The right angle congruence theorem. Again, this one seems kind of silly, but it actually saves us a step or two. It's nice to have sometimes. All right angles are congruent to one another. It's true. Now, in the very last section, there are some theorems that come up, and we'll just mention them. Vertical angle theorem. We've talked about vertical angles. Vertical angles are congruent. The theorem says they're congruent, not the definition. So you can, for a reason, it'll be vertical angle theorem, where vertical angles are congruent. The common segments theorem, I did that out of order, but the idea is if AB and CD are congruent, then when I look at AC and BD, since AC and BD both contain that segment BC, then they would have to be congruent. So just think of the numbers here. Let me make up some numbers. Let's say this was 5, and this was 10, and this was 5. What I would be saying is that 15 is equal to 15. If two congruent angles are supplementary, so they're congruent, so this one and this one are congruent. They're supplementary, so they add to 180, and they're congruent, so they must both be 90 degrees. 90 plus 90 is 180. And this last one here, we'll just mention it. Definition of perpendicular lines. Perpendicular means lines that meet at a right angle. So if this was AB and AC, they are perpendicular because they meet at a right angle. Two lines are perpendicular if and only if they meet at a right angle. Again, it's if and only if. That means it's a biconditional. So I could say if they meet at a right angle, then they're perpendicular. All right, let's look at this first little proof. We're supplying the reasons. Angle 3 is congruent to angle 4. So you got to recognize that those are vertical angles. And with the reason that vertical angles are congruent are the vertical angle theorem. So notice I'm abbreviating, using the symbol angle and abbreviating theorem, just shortening it. Angle 2 and 3 are supplementary. Well, 2 and 3, they make a straight line. They're a linear pair. That's the linear pair theorem. The measure of 2 plus the measure of 3 is 180. So a thing to remember in proof is that things follow each other. The reasoning is sequential, logical. So step 3 comes from step 2. So how do we know if they're supplementary, they add 180? That's the definition of supplementary angles. Now somehow they replace 3 with 4. Well, look at step 1. 3 and 4 were congruent. Now I'm allowing you to just substitute in. We're going to call that substitution. Substitution. Number 2. Notice that 2 and 3 have no diagram, so we don't have a diagram here. 4 is congruent to 5, and 5 is congruent to 7. Hey, look, both those statements have a 5 in them. I could replace below, in step 2, angle 5 with angle 4. I could substitute and say that angle 4 is congruent to angle 7. That's the substitution property. Number 3, we have given here. Given is what we know to be true. So 5 plus 7, those measures, is equal to the measure of 6 plus the measure of 8. Now, we also have that measure of 7 is equal to measure of 8. So these two are equal. They're the same number. So notice how there's a 7 and an 8 here. Well, I could subtract 7 and 8 from both sides because I'm subtracting the same thing from both sides. This is subtraction property of equality. The subtraction, include the R, property of equality. So if I subtract 7 from the left side, I get the measure of angle 5. If I subtract 8 from the right side, I get the measure of angle 6. Number 4, BD is the bisector of angle ABE. ABE, right here. So it bisects that angle. That means that angle 1 is congruent to angle 2. How do we know that? Well, we need to know what a bisector is. That's the definition of angle bisector. So as I write down a reason, I've got to look at my reasons and make sure I'm concluding the conclusion of each reason. And remember that a definition can be a biconditional. I can flip it around. So I need something on number 4 that concluded the angles were congruent and use the fact that I had a bisector. Well, the only thing was the definition of angle bisector. Number 5, step 1. The measure of 1 plus the measure of 2, I already diagrammed that out here, is the measure of ABE. So that's 2 angles make a big angle. That's the angle addition postulate. The measure of ABE, so that's this one here, is congruent to FBC. That's this one here. Well, it may not be obvious, but those are vertical angles. That's the vertical angle theorem. Angles formed by intersecting lines. So then what they did is they took ABE, and they replaced it with FBC. That's the substitution property. Substitution. Number 6, B is the midpoint of AC. So I need something that starts off with a hypothesis that we got a midpoint and concludes that we have congruent segments. That would be the definition of midpoint. Number 3, 2 segments make a big segment. That is the segment addition postulate. Now, somehow they have 2BC, and it came from that previous step. If we look at step 2, you see how they have 2BC? I could take and replace AB with BC. I could use step 2, since AB and BC are equal. I could plug in for AB, BC, and I have BC plus BC, which is 2BC. So this was actually substitution. They used step 2 and 3, and they substituted, and then they simplified 2. Now somehow they got a 1/2. Look at step 4 and step 5. They got rid of that 2, and we have a 1/2 on the other side. They divided by 2. That was the division property of equality. Number 7. BD is the bisector of angle ABE. Angle 2 is congruent to angle EBC. So we got angle 1 congruent to angle 2. Notice how BD is the bisector. We need something that has a hypothesis that we have a bisector and concludes that we have congruent angles. That's the definition of angle bisector. Now somehow they replaced angle 2 with EBC. Angle 2 got replaced in step 2 and became angle ABC. That was substitution. Number 4, ABF, that's that one, is congruent to angle EBC. That's that one. Oh, those are vertical angles. That's the vertical angle theorem. Then they replaced angle EBC with angle ABF, so that was another substitution. So we used step 4, plugged it in to step 3, and replaced angle EBC with angle ABF. Number 8, we got a couple of midpoints, and we have some equal segments. Now notice step 2. If you look at the picture, step 2 is two segments make a big segment. AB plus BC equals AC. That's segment addition. AB and BC are equal, FB and BE are equal. So we're using this right here. If you look, B is the midpoint of AC and B is the midpoint of FE. This comes from the fact that we have a midpoint, and then we have two equal segments. That is the definition of midpoint. AB plus BC equals FB plus FBE. So these two right here, they took and replaced AC with AB plus BC, and they replaced FE with FB plus BE. That was substitution. So they used the given right there and step 2 to substitute and say this. Now they did some kind of substitution again. They have 2 BC here, so they replaced AB with BC. And on the other side, they have BE, so they replaced FB with BE. So they substituted twice. So it's substitution again. Now they divided both sides by 2. So the last step was the division property of equality. So here are some little more obvious ones. Two segments make a big segment. That's the segment addition postulate. Number 10, two angles make a big angle. That's the angle addition postulate. Number 3, the measure of DGF, that's this one, is congruent to CGA, that's this one. Well, those are vertical angles. Vertical angle theorem. Now they did some kind of substitution. Well, see how these two are equal? So I could replace angle DGF with the measure 3 plus the measure 4. And I could replace angle CGA with the measure of 1 plus the measure of 2. So that was substitution. Now they subtracted, so if we look up above, the measure 3 was equal to the measure 2, so there's the measure 3 on this side. There's the measure 2 on that side. I'm subtracting the same thing from both sides since they're equal things. 3 and 2 are equal, they're the same number. So if I subtract it off both sides, I get the measure of angle 4 equals the measure of angle 1. On number 11, we have a bisector, and we're concluding that angles are equal. That's the definition of angle bisector. EGA and angle 1 are supplementary. EGA, let's change colors here. EGA, that's this one, and angle 1, that one, are supplementary. Though they make a straight line, that's the linear pair theorem. So if they're supplementary, then I know they add to 180. That's the definition of supplementary angles. That's what it says. It concludes that If the angles are supplementary, then they add to 180. Now they did some kind of replacement. They replaced angle 1 with angle 2 from step 2. That was a substitution. And look, I know they add to 180. Therefore, this is like the converse of what I said before. If they add to 180, then they're supplementary. That's the definition of supplementary angles again. But it's the other version. It's the converse versus the original, or the original versus the converse, depending on how you wrote it. Last couple of examples. We have an angle bisector. Therefore, we have congruent angles. That's the definition of angle bisector. FGB, FGB, that's that one. And angle 4 are supplementary. Those are linear pair. So that's the linear pair theorem. And those two angles here, FGB and DGB, those angles, they're supplements of congruent angles. So since these two add to 180 and those two add to 180 and 4 and 3 are congruent, that means those other two angles have to be congruent. Not a reason we use that much, and I probably would not put that one on the test. Angle 1 and angle 4 are equal, that's given. Angle DGF, that's this one, is equal to AGC, that's that one. Those are vertical angles, vertical angle theorem. Two angles make a big angle, that's the angle addition postulate. Now they did some kind of substitution. They replaced AGC with 1 plus 2, and they replaced DGF with 3 plus 4. There's a substitution. And since 1 was congruent to 4 in the given, 1 was congruent to 4, and since we know they're equal, we can subtract, since they're equal to the same number, we can subtract the same number from both sides. That is the subtraction property of equality. Now, this is always tough at the beginning. It's a matter of knowing your reasons, looking for the hypothesis that you need and the conclusion you need for each reason. The ones we're going to do today are much easier, but this gives you a little overview of how you use the reasons.